Alright, I'm going to be giving you a demonstration on the sample prep for running an NMR. We'll start off by talking about our NMR tube. Our NMR tube is just a glass tube and a cap. We are going to start with our unknown. We're going to add just a single drop of our unknown using a pipette. Get it in there. Alright. Have a drop of our unknown. As you can see right here, drop of our unknown. We're going to get a fresh pipette. And then we're going to add about half a ml of deuterated chloroform, which you can see right here. So our bottle, this is not cheap, so we want to not use too much. Oh my gosh, it's not fun to draw. So your first question might be, why do we use deuterated chloroform? Deuterium is a hydrogen with an extra neutron. So hydrogen, the most abundant form of hydrogen, so just hydrogen, has one proton and no neutrons. Therefore it's spin active because the sum of the protons and neutrons is an odd number. Now, since deuterium has one proton and one neutron, when we add those together we get an even number. Therefore, it is not spin active. So we use deuterated chloroform, so chloroform that doesn't have a hydrogen but instead has the deuterium. We use that so that when we lock onto the signal and when we run our sample, we aren't overpowering our sample data with the peak from our solvent. So we would like our peak from our sample to be greater than the peak from our solvent, so we use that. Another thing to take into consideration, I only used a single drop of the unknown, and then I used about a half a ml of the deuterated chloroform. I could get away with using just a small amount of my unknown and having it in such a low concentration because, like I said, hydrogen, the hydrogen that's in my unknown, is naturally abundant and naturally spin active. Now, if I were to want to do, let's say, a carbon-13 NMR, I would want to make my sample mostly my unknown and just add a little bit of chloroform. I would want a higher concentration of my unknown for carbon-13 NMR because carbon-13 is the active nucleus of carbon. But it's only 1.1% naturally abundant. So we would need to use more of that. I think that concludes our sample prep. Now you can go on and learn how to run an NMR. Hello, this is a brief tutorial on how to work our NMR machine. We're using a Bruker 400 megahertz. So we'll go ahead and get started. I have my sample right here. Recall that our sample today is going to be deuterated chloroform. So the first thing we need to do is put our sample, our NMR tube, into the spinner, which will then go in the machine. This is the thing that holds our NMR tube in place while it's in the probe. We will push this down so that about the center of our our sample goes through this line. In this case, we have quite a bit of sample, so we can put it all the way to the bottom. Once we push it to the bottom, we're going to pull it up ever so slightly so that when it goes into the machine, it doesn't push down too far. The next thing we're going to do, so we need to get the sample in there. So we're going to click lift, and that's going to allow air to push up through the instrument and allow a place for us to set our sample. So we're going to walk on over here. We see this yellow chain that's blocking the instrument. This is the range. This is called the 5 Gaussian line. We don't want to cross this without it with electronics or anything metal in it. So make sure you're free of those things before you step over. We're going to take our sample. Once we hear the air kick on, we're going to set our sample here ever so slightly. We're going to feel how it holds it up. You can see it's holding it up there. Now we're going to walk back over to our machine, or our computer, and we're going to hit lift again, and that's going to drop the sample down. Now, it's important to know that our instrument here has a magnet in it, and this magnet is kept cool by liquid helium, and then that liquid helium is surrounded by liquid nitrogen. We have to cool our instrument, cool our magnet so that, because when it warms, it can lose its charge, and then we have to recharge it. So it's very important that we make sure we have our liquid nitrogen filled and our liquid helium filled, and that's taken care of by our instrument expert. All right, so moving on to our the computer aspect of this. So first thing we need to do is open a data file so we can save. So we're going to give this a title, so we'll call this sample 1, and then it's always good to include the solvent. In this case it's deuterated chloroform. And we are going to look here for our experiment. What type of experiment are we going to run? We're going to run a proton experiment here, so we have that selected. Then we can set our solvent. Our solvent is, again, deuterated chloroform, so we have that here. And then we're going to go OK. All right, the next step is to lock. We call this locking. Essentially what we're doing is we're telling our instrument what our solvent is, and the instrument is then going to lock on to the signal given off by our particular solvent. So it has some sort of reference point. The next thing we need to do is get to get our sample spinning. So we hit spin. One thing that's good to know is this red right here indicates that it's working on doing whatever command you've told it to do. Once it turns green, that means it has finished that command. So a little bit with the actual interface we have here, we have 3 screens. We have the screen that we see our spectrum on. We see a lock display, so right here. So this is where we can kind of see where we're locked at. And then we have the control suite, which allows us to lock and spin and such. The next thing we need to do is tell the computer to, or tell the instrument to automatically tune and match. So we call this ATM. We are in this process tuning the frequency of the NMR probe to to the selected nuclei. And in this case, we're using hydrogen. The machine will, or the instrument will automatically rotate the sample tube inside the probe to get the most consistent reading. The next step is to shim. So in shimming, we are moving the magnetic field in the X, Y, and Z directions in order to make the local magnetic field homogeneous. So we want to ensure that from each angle that the magnetic field goes in, it's the same for where our sample is located.
Okay.
Alright, the next step is RGA, or receiver gain step. This sets the sensitivity of the instrument based on the concentration of the sample. Recall from the sample prep video that when we prepped this sample, we have a low concentration, so it's adjusting to account for that. And then the last step is ZG. What we call it, and ZG is running. So we start collecting data from the machine. Sometimes we can look down here at the bottom and see where our scans are and how much time is left. So you see -1. So sometimes we have some dummy scans in there, so the instrument takes some scans before it starts actually taking the data, because sometimes the first and second scan aren't good. So right now what you're seeing is the unaltered data, so just how it's coming out of the machine. We can get the data, or get our spectrum to look like what we see in our textbook by using Fourier transform. In Fourier transform, it's a way to analyze your data. It's the same sort of technique done when we do IR, so FTIR. So we've almost finished. We have about 10 seconds left, and then we can begin analyzing our data. When we analyze our data, we're going to do two things. We're going to do one thing called integrating. So when we integrate, we have this integrate tool, and what we're doing is finding the relative, or the area under the peak, and we can do this with several peaks, and then we can compare the number given by the area under that peak to give ratios of hydrogens per peak, which can be a handy tool. The next thing we might do to analyze our data is called peak picking. So essentially what you're doing is you're locating your peaks and determining what the chemical shift is, and then marking it on your graph, so you can refer back to it later to analyze the chemical shift.